My name is Cesare Garlati. I'm with X5. X5 is a young software security startup that started just to serve the RISC-V space. So we are big believers in open source and in what RISC-V brings in. So today I'm going to spend a few minutes talking about mixed criticality systems. What are these things? Well, these are systems where you have multiple trusted workloads or applications that, for many different reasons, end up to work together on an untrusted platform. And so this is happening more and more. What you see there is obviously a drone. This is happening in automotive, is happening basically in many different places. You have this trend to put things together to minimize the cost of hardware, whatever is the situation. But at the same time, you end up having safety-critical pieces of your functionality that collides with something which is not that trustworthy. And we will see what it means and what can be done about that, right? So what is not trusted is anything which is big, okay? So this is not about being smarter or better or whatever. It's just about being bigger. And this is the code base. I have a slide in a minute that shows you a little bit of the math behind this, but the concept is very simple. In security, less is more. The more you add, the less security you get, okay? So Linux, you'll see the slide, it's quite big. Real-time OS might get biggish, but definitely some legacy OS and platforms and system-level software is definitely too big to be trusted, okay? Now, something else is happening is this multi-core, 4 cores plus 1, 8 cores plus 2. And that's good, that's great. But the idea that then you carve out secure execution environments inside the very same core is probably not that good of an idea. I'm going to show you why in a second. So I have 8 cores. Can I put 6 different applications on each one of the cores? Yes, you can. Now I have 2 cores. Can I put 6 safety-critical pieces of my application on the same core? Probably not a good idea. And we'll see in a second. For people familiar with RISC-V, it boils down to be mainly about the M mode. M mode is the highest level of privilege. And once you have any piece of software that runs at that level of privilege, well, you have to trust your whole core with that software. And so, for instance, to be specific, Linux has something that we are working on, as you know well, which is the SBI, this interface that runs at the most privileged level. So that's big, and the implementation depends what it is. Can that really be trusted in the very same core? L1, L2 is the whole issue with caches, right? So once something ends up in the cache, bad things can happen. So how you actually partition the cache so that you're sure that you're not giving up your secrets or getting something that you don't want in. And you will see in a second how we do that. Now, a couple of more interesting, I think, more innovative kind of things to discuss is the concept of zero trust. For companies that build these kind of objects, and by the way, we have the very architect in this room, and that will be in the next presentation with Kevin Kinsella, don't miss it. He will tell you that they have so much of an extended supply chain that it's simply impossible to get all the pieces in place and start talking about what I trust and what don't. So the concept is diametrically opposite. They say, let's start by assuming that everything is broken and corrupted or exploited, and see how we can build a system that still works even if pieces might not be working as expected. The typical examples are drivers in Linux. We love Linux. I run Linux, and everyone loves it. But if you know, drivers run in kernel mode, which is the privileged mode once it turns into a processor. How many people have a Wi-Fi laptop in this room? Everyone, come on. Yeah. So how many people have Intel Wi-Fi chipsets in their laptop? Everyone. How many people are running Linux on that laptop? A few. How many people know what the code of the driver is running kernel mode is or what it is doing? No one. That's the right answer. That is called non-free. Non-free means that you don't pay for it, but you don't get to see what you're running. I picked Wi-Fi just to make an example, but any piece of hardware, any kind of possible box that comes from a vendor and you don't get to know what's in there, it's a potential avenue for attack. Okay. And I have the people who teach me this in the room, right? So anything which is big, which is thick, is where the whole security story a little bit gets lost. Not to say that big pieces of software are bad, it's just that when you really need to trust your system with something which is critical, you need to have something small. That's the end of the story. And you can have anything else in addition, that's fine, but where the security, where the trust is, has to be formally verifiable, very thin, minimal. Okay, so let me start this slide by saying that I'm a big supporter of Linux, open source in general, but Linux in particular. We develop on Linux machines. We use also for personal computing Linux. We are on Debian. So this is not about saying bad things about Linux. It's about sharing some numbers. And the numbers, I invite you to double check them online, are the code size or the code base size. So this is a free utility that just points to any kind of version of the kernel. This is just the kernel, okay? And tells you how many lines of code are there. So last time I ran this one was 17 million lines. It's probably a little bit more now. And by the way, this is just the kernel. The kernel per se does nothing. You need to add some number of millions of lines of code, right? And eventually they are very good lines of code. That's not the problem. The problem is that if you do a little bit of research, or you've got some of these classes in school, whatever is the situation, you know there is a statistical relationship in between how complex is a system, in the case of software, how many lines of code are there, and how many defects or how many things can go wrong. And if you run the math, and you apply the best ratio I could find, please find a better one if you can, but I found this. So the third example is one defect every 10,000 lines of code. And I think that is the methodology used for the software that runs the space shuttle, the most complex machine ever built on Earth, okay? So assuming the best possible scenario and just running a multiplication, basically, I can tell you that I would expect 1,700 bad things happening to any Linux kernel out there. It takes one of these bad things to take down one of those boards that I show you in the first page, okay? That's a risk that is simply not acceptable. So what do we do with RISC-V? Well, we have good ammunitions there. We have good building blocks. And so I'm going to show a couple of major ones. So one of those is security, let's say, privilege levels, even before we get to security, right? In other platforms, these are called the rings. Here we call them privilege modes. We have 4. That's good. They might not be all the time available. If you have a Linux-capable core, you have the S mode. And then for sure you have M, which is there, otherwise it's not a RISC-V core. The interesting story becomes when you start adding U, user mode. And user mode can be combined directly with M. And so if you have M and U, you don't have the MMU, but you have a securable core. And we will see how this fits the bigger picture. And hypervisor, we have the people in the room. We are working on the standard. It's coming, it's coming, it's coming. That's the 4th level, eventually, the hypervisor level. Now, as a complement to the privilege modes, this is all in the specs, so no need to take pictures. You go online, download the file. It's 1.11. It's a nice PDF, well done, okay? So the complement to the privilege modes is the physical memory protection, which is not the end of the story, but is a starting building block. It has to be there. Otherwise, there's no story about securing anything in terms of providing separation within the hardware itself, okay? Personally, I'm working with different platforms, and I think RISC-V has done a very nice job. It's clean, it's nice. Let's not mess it up, please, people who belong to those groups and so on. That's not that stuff that is not needed. What we have is working. It's commercial grade. It's up there in the booth. Check it out. We have done this out of the specs. It works. Can be improved? Well, everything can be improved. Do we have something that is enough, good enough? I think it is. I'm not going through the old details, but if you start playing with the complexity of physical memory protection, that's when you will discover soon that that's why it's typically not used. It's very complex, okay? Already. How many know what's NAPOT here? N-A-P-O-T. No, everyone should know, otherwise you cannot. So only 2, right? It's natural 9 power of 2. I'm not going into the details, but just to give you an idea, if you want to deepen your understanding of these building blocks, those are 2 good starting points. Okay, so what do we do with these ingredients? How we actually bake the cake? So it's a real example. Again, anything I'm showing to you is not research. It's commercial grade. It's down there at the booths. You can go and please come back and check it out. This is working on real hardware, real software, and so forth. So this is the first incarnation of a RISC-V Linux capable system. There are 4 cores on the right. It's SMP, so you can use 4 of them for Linux, 3 for Linux and 1 for Zephyr, whatever is the thing you want to do. But what's most important, on the left side, we have an MCU core. And that MCU is exactly like the other cores, just doesn't have the MMU and the level of privilege that goes with the MMU. That's the perfect place to start dealing with something reliable, deterministic, and really to get a hold on your system in terms of safety critical. And so here is what we can do if you know what you're doing, or if you have tools that allows you to do that, or if you have supporting software. What we propose is called MultiZone. You will see in a minute, but nothing prevents you from doing this yourself. You can carve out those crypto boundaries, those red lines. And in fact, what we are showing here today, and we announced 2 days ago with a press release, is 4 secured zones. We call them zones. It can be 8, it can be as many as you want, on that core that stays on a side, that are completely isolated among themselves and with the cores that run out there. I don't have much time, so I'm going to go fast on this. But the idea is that you have something that is completely deterministic on your left side, and something that you have to assume is already broken, even before you ship it, on the right side. Okay? How you actually get the system to work securely. What you get if you apply this kind of technique is a number, whatever you need in the system, of equally secured zones. So this is not the concept of secure word, non-secure word. They are all equally secure because they are all equally isolated. And what you can do is to start mapping individual components of your SoC. This is not just about program of data. It's anything which is memory mapped. That's the way it works. So if you have peripherals, as you have, if you have drivers that run peripherals, drivers run in user mode. So they are secure by definition because they cannot do harm to the system. Now, this is enforced by the hardware through that PMP and privilege mode mechanism. So this is not voodoo or black magic. This is as solid as it gets, but it's flexible as any other piece of software. And you will see in the next slide what it really means. It's extremely lightweight, and it's open source, by the way, very important piece of it as well. Why it's important to be that small is that at this level of thickness or thinness, it is formally verifiable. So this level of trusted execution environment can be formally verified as you would formally verify your hardware itself. As I say, this is the only commercial available today for people who are getting into production. And you'll see in the next slide how easy it is to configure and use. And there's no need to change the software. There's no need to recompile. There's no need to link. There's no need to do anything if not to write one single file. I'm going to show you in the next slide. Okay, keep this slide in mind because I'm going to show you in the final one how you get this kind of separation in place in your system. Here is how you do it. You write that file. It's one file. It's not source code. It's not any magic, anything, programming, anything. It's plain English. Use your editor of choice. So what tool chain do I need to do that? Word, Microsoft Word. Write it as you want. If you can write that thing there, you are securing your system. So what level of deep knowledge of PMP do I have? You don't need any knowledge of PMP. So here is how it works, and I don't have much time. Again, all this is real. Stop by the booth, any of the 3 booths where this is being shown right now, or attend our tutorial tomorrow. We're going to spend 90 minutes to actually build all of this piece by piece and play with it. So it's as real as it gets, okay? So just for the first one, if you remember the 4 zones there, that's what it takes to secure it. It's a policy, and you say, here are the pieces of the hardware that I want to associate to that zone. And so it's a set of contiguous memory regions, and that's easy to see there. But pay attention to the right side of the slide, of the file. You can also associate policies, which now gets really interesting, right? The policies are read, write, and execute, right? Or any combination of those. So the typical classical attack where you try to put some executable instructions into your buffers and then get the processor to execute and jumping into it in any kind of different way would not work. Well, something may be fetched from memory, but because it doesn't match the execution policy, it will not be executed. And you can see how all the variations on this theme, how it works, right? Now, pay attention. Some of these ranges are not memory, are in fact memory mapped resources. the UART, any kind of physical I/O that is into the device. See, this is not about memory, it's about the whole SoC. Now, if you can write that file, what you do then, you provide your fully linked, completely independent binaries for those zones. They can be built and with different programming languages, using different compilers, different versions of different compilers. In fact, they can come from different third parties. And that's what people who put together these big systems really care about. You don't need to trust them. In fact, you don't need to know who they are at that point, as long as you maintain the separation. Anything can still go wrong in each one of these zones. There's no magic there. But that will not affect the rest of the system. And that's where the safety critical aspect of this kind of solution really plays a role. Now, for zone, for binaries, the nano kernel, which is this separation kernel, these 2 kilobytes of software, 2 kilobytes, not 2 megabytes. How do you build anything which is 2 kilobytes? You write it in assembly. See the color of my hair? Gray and losing more. So it's not fun. But that's how you get zero dependencies. So this software doesn't even depend from the C library, doesn't even depend from the C runtime, doesn't depend from anything. And that's the whole point of securing something, right? It's more difficult, but you get something better out of it in terms of size and resiliency. And now the policies that you see there is this file, basically. Right? So we have a little utility that pulls all of this together, but most importantly, signs it and puts it in the flash, okay? So that's how it works. You have pieces of binaries that you don't necessarily trust, or legacy code, you lost the source code, whatever is the situation, third party. You break the system in pieces. There is a messaging system that allows the system to work as a whole, otherwise it would not work. Run this utility, which is super fast, is a toolchain extension. It's something that you put in your make file, and what you get out of it is a signed image ready for flash. Now, whether you have secure boot, and this is measured and eventually verified by some previous steps in your booting process, or it depends on the application. But the point is that if you try to mess with any one of these settings, even 1 bit, it would not work. It would stop, okay? Now, this is my final slide, because I want to leave a few minutes for questions here. This is not fantasy. We've been hard proponents of this as a standard for adoption in the RISC-V, so still a lot to define and work on. There's plenty of details available. Everything is on GitHub. Everything has been documented. It's very permissive licensing, but the physical incarnation is what you see there, which is at the show floor if you want to take a look. That's the first Linux-capable hardware that we have seen in RISC-V. It's been there for a while. It's a micro-semi component that will become the PolarFire SoC, has been announced in the past few days. It's as real as it gets. What do we do there? We show a demo where we go through the Linux side of things, which is through an SSH connection in the Ethernet port, and then you have Linux. Okay, cool. What you do with Linux, you actually connect and get access to the first zone. And now the first of these 4 zones is just a device driver in Linux. It's as easy as it is. But anything that happens in that zone stays in that zone. It's not affected by anything else. In fact, you can completely reboot the other Linux cores. Nothing would happen to this one on the left side. And then we shoot the same for a third zone, okay? As I said, I have very limited time, so I can only give you the sense of what it is, but I have all the time in the world if you come there and take a look at the real thing. Actually, I have 2 colleagues there showing 2 different pods what this is about. I think I have 30 seconds left, but good news, we have 10 minutes break in between. So if you want to ask questions, please do it right now. And eventually, I'm happy to continue during the break. How do we manage the questions with the microphone? Is there a moving microphone? There is not, so I think you have just to yell.
You showed us MultiZone.
That's an excellent question, and I think I can recap as what are the hardware requirements for this kind of things to work. Okay, there are 2 requirements. It's out of plain RISC-V standards, but one, you have to have physical memory protection, which is completely standardized. Every vendor has it. So this approach is completely vendor agnostic. It works on, you're not locked in any of those cores. Right? You can move it around. So PMP, physical memory protection. That's the requirement number 1. which is, by the way, available in any decent core out there, okay? The question is, how many registers of PMP do I need? Well, the specs says 8 to 16. The good news is that we develop an extension at the software layer that gives you unlimited number of regions per zone. So we overcome via the runtime the number of PMP entries. But the short answer is at least 8, 16 even better. In the ARM world is always 16, that's okay, just to give you a sense. The second requirement, which typically goes with the PMP, is the user mode. If you don't have a way in an MCU class kind of device to have 2 separate privilege modes, well, that's not securable. So short answer, you need PMP, you need the U mode. Good news, they're always there, unless you're dealing with something that is not securable by definition. Thank you for the question. Next one.
To follow up on that question, so those apps that you were showing, they run at U mode, I would assume?
Exactly. That's the definition of secure. It's not secure because it's smarter or better. It's just it runs in a state of the processor that cannot create damage outside the container. So,
Just to follow up on
yes? Yes. So let's see if we can, oops, there's something else here. Okay, so I guess I cannot go back to the slide. But, so if you remember that slide, the yellow part, which is the 2 kilobyte of runtime, provides a number of components. One is messaging. What is messaging is a mechanism to replicate the behavior of the APIs. We are all familiar with APIs. You put something on the stack, you make a call, and something else comes back. Well, but that's not secure because you are sharing memory. That's a vector of attack. So there's no stack here. The zones don't have a common stack. They, in fact, are not connected. So the messaging system is a mechanism to send any byte stream across zones. It's like TCP/IP if you want, but it's small scale inside the code. It's provided by the kernel. And the second part was the question?
Yeah, you answered my question.
Yeah, so messaging is the secure way of doing APIs calls. It's based on a mechanism of core exceptions, so there's no shared memory. Basically, the system triggers an interrupt, and something happens in the core. This is intercore. In fact, the IPC is not interprocess, it's interprocessor communication. There's no process at that level. These are very good questions. Thank you.